Okay, let's solve problem B. In this problem, we actually need to solve two different cases when it just asks us for the answer and when it asks for a certificate too. So let's start from here. Consider that you have some 1 bits and some 0 bits, and you want to order them in a way that the sum value that is defined here is minimum. So you can play and try, and what you will find is if you group ones in groups of size, in blocks of size even, like this, they all will lead to the minimum answer. So for this is minimum, this is also minimum, this is also minimum, this is also minimum, and so on. So this is for the case that we have some even number of ones and some zeros. But what happens if we have some 1, 2? In that case, you will see that at least this is a solution that you come with 1, and then you will come with some zeros and ones, again with the previous condition that groups of ones, like blocks of ones, are even sized. Like this is a minimum x sum of this sequence as this is, and as this is, and for sure as this one is. So now let's solve our problem. So what we understand from this problem is you have to print n integers 0 to n minus 1. So let's start with the most significant bit. So the most significant bit will have, so some numbers will have 0 in that place and some other numbers will have 1 in that place. So we want to group the numbers that have 1 in that place in groups of even, which is if we order the permutation from 0 to n minus 1 and don't change it at all, it will follow that. So let's start with an example like n equals to 8. So it's this, right? So in this example, what do you see? You see that for the most significant bit and also for the second significant bit, the groups of 1 are even sized, like this. These 4 were like this. These 2, right? The only exception is the least bit, I mean the rightmost bit. These bits actually flip every time, so 0, 1, 0, 1, 0, 1, and so on. So what we do is very simple. We swap these numbers and that's it. Now if you look at these numbers, these bits, all of ones are stick together as even sized blocks. And consider that we have another, or like we don't have this one, so n is 7, then yeah, that's true that this block is not even sized, but still it follows the rule that we said. One of the ones is at one side and other ones, they have block of even size like this. So that works, that is still working. So what we are gonna do here is just printing numbers 0 to n minus 1 and swap these numbers to make sure that they are stick together, the odd numbers are stick together to make odd blocks. And next part is how we want to deal when it wants us to print the answer. So C2, the second type of query. So for that, we need to count for each bit the number of ones the numbers have in this bit, and then move those ones to the left, for example, and zeros to the right, and find the answer, and finally sum up these numbers together, and that's it. So, for example, consider n is 7, and we have c equal to 2. So let's consider the second bit. So first bit is the least significant bit, and second bit. So for second bit, let's count how many ones we have. For counting that, first, what we do is dividing n by 2 to the power of 2. Then we multiply all these numbers to 2 to the power of 1. So it's like if we want to count numbers from 0 to n, that they have 1 in their bit bit, we can follow such formula. So what we understand is, let's numerate bits by 0, 1, 2 like that. So 0 is the least significant bit and 1 is the next one, and so on. So if you look at them carefully, every 2 to the power of b plus 1 numbers, they will make a new cycle. So its period is 2 to the power of b plus 1. And tell me, how many of these numbers have 1 in this place? I mean, the base bit, 2 to the power of b, right? So what we do is dividing this by this, and then multiplying it by 2 to the power of b, and finally we calculate how many numbers remain after we divide, okay? And we know that, so consider a new cycle started, a new block. So the first 2 to the power of b numbers, they have 0 in that place, and then 1 starts. So it's like, consider some, let's say b equals to 1, for instance. So consider some number like this. Then the next number is this, the next number is this, and finally this one, and then this. So look at this bit. The bit numbered 1, 0, 0, 1, 1, and again 0, and it will repeat. So it will repeat like 0, 0, 1, 1, 0, 0, 1, 1. So as we say, the length of blocks, the length of period of this bit has length 2 to the power of b plus 1, which is 4. 1 plus 1 equals to 2. 2 to the power of 2 is 4. And as you can see, after 4 bits, it again starts with the fresh start, like 0, and again 0, and again 1, 1. So that's why I divide n by this and then I multiplied it by 2 to the power of b. Why? Because in every block of size 2 to the power of b plus 1, 2 to the power of b of them have 1 in that place. Then I calculate the modulo to find how many numbers we have after starting the fresh restart of the last block. And then I minus it by 2 to the power of b, because first to the power of b numbers are useless. And don't forget to get max, because this number can become negative. So we need to take care of that. So for this problem, I'm gonna use Python, because it would be much easier to handle everything here. And let's do it. So okay, we have test case, we read test case, and then we have C and N. And then if C is 1, what I'm gonna do is, as I said, I will swap some numbers to put 1 in the correct place to make even sized blocks of 1. So let's make our permutation, and then the numbers we are gonna swap are the numbers at index 2 and then 6 and so on. So for I in range 2 to n, and if for every 4 numbers, what I'm gonna do is swapping AI and AI plus 1 with AI plus 1 and AI, and finally I print A. And first let's start by testing this, because I need to make sure this will work. 110, let's see. 0, 1, 2, 3, 4, 5, 7, 6. That is working. But let's also, what's happening? For 7, it's going outside of the range, so let's do this. This is actually not working. Why? Because we need to also swap 5 and move it to the end, because I told you that numbers, when we have odd number of bits, we need to have one of ones to one of the beginnings. Actually, other cases can be accepted too, but this is safe. So let's do that. So to do that, I think we need to put some if here. If n modulo 4 is 3, then a minus 1 and a minus 2, replace them, actually swap them. So let's try, and then 8, and then 9. 9 is good, 10 is good, 11 is good. Okay, that's it. We found the answer for this case, I think. We'll see after we submit, actually. So, the next case. So the next case, we loop over bits in range of, let's define big B here. I do this, and first is 0, then and plus equals. Let's copy paste from here. First we divide n by, so I think that we need to decrease n by 1 because I'm including n itself in my formula. So let's see what happens, and if it was wrong, we'll replace it, and then like this. So this formula will count for us number of set bits in this bit, right? So okay, let's test that function before we proceed. And we return this. Now let's print here. Let's print count of, like, for example, 7, and first bit it says 3. Clearly wrong, right? Because for 7 in the first bit we have 2, and then another 2. Maybe it's okay. Let's count for 8, 4 for 6, 2 for 4, 2. Good. Actually, it's not including n in itself, so working exactly as we want. So yeah, okay, great. So one is count of n and b, and zeros are n minus 1s. And now we want to calculate the x sum. So we have some 1s and some zeros, and we want to calculate the x sum. So x sum would be number of sub arrays in this array that they have odd number of 1s in this range. Good. So we will calculate the number of these subarrays. To count such subarrays, what we do is this. So first, let's start with counting subarrays that are inside the one block. So we have a 1 block here and zeros block here, and we want to calculate the number of subarrays that are fully inside the ones. So consider something like this, these ones. So how many good subarrays start from this bit? 1, right? What about this one? 1, right? What about this? 2. 1 is this and 1 is this. What about this? 2 again, then 3, then 3. This is also 3. 1, 2, 3. So if we have the number of 1s, the answer of the number of subarrays inside this block is 1 plus 1 plus 2 plus 2 plus 3 plus 3 and finally plus 1 divided by 2. So what we do here is adding to the answer. Let's define another current answer to be 1 divided by 2 times 1 divided by 2 plus 1, and don't divide it by 2 because we have 2 of each number. But this is for when the number of ones is even. What about when it's odd? So when it's odd, it's like this, right? And what we are calculating is, so 2 times 3, which is 6, and we are calculating this, and we need to add 3 2. So if 1 is odd, we need to add to our current answer 1 plus 1 divided by 2. That's it. Or that is also easy. Then let's count the number of sovereigns that start in ones and end in some zeros. That is much easier. So you need to pick odd number of ones from here, that you have 1 divided by 2, 1 plus 1 divided by 2, because we want to get tail times zeros, that's it. So current ends plus equal, and that is easy. So this is the answer for this bit, and we need to multiply it but by 2 to the power of b. So ends plus equal current answer multiplied by 2 to the power of b, and finally print the answer modulo mod, which is 10 to the power of 9 plus 7, right? Right. And now let's try. Oops. This is very bad. What is happening here? Let's see. Uh, so first reduce number of bits to 4, and then print 1, 0, and 1, and then reduce the number of test cases to 1, and it's saying all 0, and when it's 0, why it's adding something to the answer? Let's print this too. Okay. So n is 1 in our test case. So, oops. Okay, it's saying that you have 1, 1 in this bit and also the next bit. So let's print count of 1, and the first bit, it's 0. So what about this? This is also. Why? Sorry, zeros is 1, not 1. Okay, I was making a mistake. So, but why current answer becomes 1? So this seems, this is 0, this is also 0 multiplied, so this is the bot. It is fixed. Let's run again. This is good to go. This is good to go. I'm gonna submit. Okay. 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 Let's submit to see what happens. What? Oops. Run compiler. Sorry. Submitting again. Okay. Wrong answer on the first test case. So it says that 0 to 1 is not good answer. Let's say why. So 0 to 1. 0 to 1 and 2, 0, 1. Let's calculate answer for each of them. 2, 0, 1. First, let's take 2, 0, which is 2 plus 2 and 1, which is 3 plus this, which is 1. Then let's take my answer. 0 to 1. 0 to 1. It's 2 plus 3 plus 3. Oops. It's correct. So I made mistake. Where? So let's come with the binary version of these numbers. Oh, that should be put aside, but I'm not putting that. You see, this number should be put aside, but I'm not doing that. So, this is that case. So 0 to 1 is good. 0, 1, 2 is good answer actually, but let's submit again. See what happens. Again, we have right answer. Let's see. It says that 0, 1, 2 is not good answer too. Got it. So we need to be more careful with this case, I think. So for this case, let me think a bit. I have an idea. Let's try it. I was doing some experiments, and based on this, we need to move the second last number to be the beginning of the array. So it will be like this. So we move the second last element to the beginning of the array. it needs to work also for 7. So let me try 7. It's like 0, 1, 3, correct, then 2, then 4, 5, 6, but 5 goes to the beginning. That is true. Let's submit this code to see what happens. Okay. Are we going to get time limit exceeded? Yes. But what can I do? So it seems super optimal. Uh, maybe we need to translate this code to C++. I'm not sure. This is for sure not a problem. Yeah. And this is also very fast. And we also use PyPy. So and maybe the answer is getting very large, but I don't think so too. Let me try a bit and we will continue. Okay, I translated that code to C++, and now we are gonna submit again. C++, and we are gonna submit again, like this. Let's see. Okay, we got accepted.
Thanks for watching. If you found this video useful, please like, subscribe, and ring that bell. By the way, YouTube thinks the video down here is just perfect for you. Give it a watch and let me know in the comments.